Extra, extra, read all about it. We have a national math epidemic. A math disease appears in 3rd grade and children have not been immunized. Symptoms include stomach ache at math time, tears while working on flashcards, poor grades on math tests, expressions of "I hate math," and low self-esteem due to constant failure. When left untreated, these symptoms have serious consequences. Discouraged children, kids who drop out of school and lose their dreams, kids who can't get into college. Some people never recover. Don't wait until 3rd grade. Immunize your children beginning in preschool. The prescription is 4-group math. What causes the math disease that plagues our country? The common methods for teaching children about number do not make sense to all children. Let's look at some of those. Children have their fingers. They are taught to count on their fingers. Dominoes, playing cards, and dice are used for math games. Base 10 blocks. A unit block is 1. 10 unit blocks connected together make a 10 rod. 10 10 rods make a 100 square. 10 frames, where this is 1, this is the pattern for 3, 5, 8, and 10. But these are the faces on many children when it's time for math. And let's look at a reason why. You cannot put the 1 with the 5 on dice and make the pattern for 6. The same is true with playing cards. 4 and 2 do not make the pattern for 6. So visually, these patterns for math don't make sense. Something is missing. At Kusky Math, we have developed a set of number patterns that fit together like a puzzle. We believe we have found the missing piece. The 4-group number patterns. We evaluated the effects of the 4-group number patterns in a 1st grade mathematics curriculum. We replaced all visual patterns with the 4-group number patterns. Pre- and post-testing of children using the 4-group number patterns showed significantly higher scores over a control group. And as important as test scores is the qualitative feedback. Math is fun. Why a 4-group method when we are a base 10 number system? As contrary as its name may sound, the 4-group method is base 10. Let's look at the science that's behind the 4-group method. The 4-group method is based on an ability that is present in every child. This ability is called subitizing. It's generally defined as the rapid, accurate, and confident judgment of the quantity of a set of objects without counting. Let's try it. You will see a number of dots for a fraction of a second. Do not blink. How many did you see? Are you confident that you are accurate? Let's try again. You will see some more dots for a fraction of a second. Don't blink. How many did you see this time? Are you confident that you are accurate? One more time. Keep the 4 in mind, and you will see some more dots for a fraction of a second. Do not blink. How many did you see that time? Are you confident that you are accurate? Let's review. How many was this? 4. How many was this? And how did you know it was 8? Did you see the 2 groups of 4? How many was this? And if I ask you, are you sure? What do? You count. The only way to know is by counting and recounting, or taking the time to group and regroup. Research shows that young children can subitize 4 objects in a square array. They cannot subitize linear arrays greater than 3. So when we take objects and put them in a row for children, they're fine when there are 3 objects. But as soon as we add that 4th one, and then the 5th one, we really lose kids in being confident that they are accurate of how many they see. The 4-group method builds students' math knowledge on their innate ability to subitize 4 items in a square pattern without counting. We tell kids, use your math eyes. Of course, we all know that children must learn to count linear objects, so kids can count these. And then the 4-group method gives them a way to self-check the accuracy of these counts and build confidence. So they count the objects and then move them into the 4-group pattern and see with their math eyes that they have 6. And they are sure that they have 6. 4-group math uses a set of 4 group number patterns that are made up of the following 4 subitizable component parts. And it doesn't matter if the parts are connected, as in these blocks, or if they're just items arranged on the table. What is important is the configuration of the items. So we take those 4 subitizable component parts and we make the larger numbers. 5 is 4 and 1 more. 6 is 4 and 2 more. 7 is 4 and 3 more. 8 is 4 and 4. 9 is 4, 4 and 1 more. And 10 is 4, 4 and 2 more. This makes it possible for children to conceptualize the quantity of each of these numbers.
1, 2, 3, 4. 4 and 1 more make 5. 4 and 2 more make 6. 4 and 3 more make 7. 4 and 4 is 8. 4 and 4 and 1 more is 9. 4 and 4. 4 and 4 and 2 more makes 10.
So this is our number parade, showing the numbers 1 to 10. And then we have the numbers 11 through 20, where the 10 is all blue and each of the ones is all orange.
Count safely. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 1, 10, 2, 10, 3, 10, 4, 10, 5, 10, 6, 10, 7, 10, 8, 10, 9, 10.
This preschooler is matching 20 with 2 10 blocks. We often see this kind of a number parade in homes or in classrooms. It's very difficult for kids to understand the numbers. Let's meet 10 Man. He helps us conceptualize the quantity of 10 in a fun and engaging way for children. He's a very special snowman. He shows us that 10 is 4, 4, and 2 more. He has 4 on the bottom snowball, 4 on the middle, and 2 eyes. When he winks, he's 9. When he sleeps, he's 8. Notice that the numbers on 10 men start at the bottom and go right left. Our base 10 system of writing numbers writes larger numbers to the left. So counting like 10 men, getting larger to the left, is a helpful foundation for later understanding of place value. We have 9 ones. We get 1 more. That group moves to the left and becomes 1 group of 10. When we add numbers, we put the new group to the left. So 8 and 4, we put the 2 ones and carry 1 10 to the left. We're trying to get kids to think how our number system works. By giving children a set order for building their numbers, they can stop at any time and see the 4-group number pattern for the quantity. They don't need to count. Now they can see they have 5. As they continue, they can stop and see they have 8. And now they have 10. If children were to build in a linear arrangement, they would have to count each time to see how many they had. Counting like 10 men is easy.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Now let's compare the common 5-group visual model and our 4-group method when it comes to adding numbers to 10. This is a 5-group 6 and a 3 and a 3. You can't put the 3 and 3 together and make the 6. You have to break one of the 3's into a 2 and a 1 to match the 6 pattern. In the 4-group method, 3 rotates and goes together with the other 3 to make 6. Here's an example for 8. 4 and 4 cannot make 8 unless you split a 4 into a 1 and a 3. In the 4-group method, 4 and 4 make 8, 5 and 3 make the same 8, 6 and 2 make 8, 7 and 1 make 8. And this is true of all the 4-group patterns from 1 to 10. Children see this example in common math curriculums. They must count all the objects to find the total. In the 4-group method, it looks like this. They see a 4 and a 3 and put them together to make the 7 pattern. Here's an example where the children must identify the quantity of each fruit. So they count the apples and find 6, count the lemons, and then count all the fruit to find out how many. With the 4-group method, they can see they have 6 and 2, combine them, and see they have 8. This is an example in a common curriculum of partners to 10. The kindergartner draws a line to make 1 and counts the rest. And they count 8. We know that's not right, but the kindergartner doesn't know it. In the 4-group model, there's 1, and we say use your math eyes to see the rest. And they see 9. Here's the same problem for 2 and 8. This time the child counted correctly. And in the 4-group model, 2, use your math eyes, and 8 make 10. These blocks show all the combinations of two numbers that make 10. 9 and 1, 8 and 2, 7 and 3, 6 and 4, and 5 and 5. This kindergartner is making her combinations and practicing ways to make 7. And this kindergartner was writing her equations for making 8. Let's look at place value, represented in the four-group method. This is the pattern for 11. This is the pattern for 22. This is not the pattern for 33. Can you see what we might change in this pattern? That's right, the 3 10s need to look the same as the 3 1s. It's the same visual representation. 3 100s has the same pattern. So if a child can add 3 and 3, they can add 30 and 30, and 300 and 300, with the same visual image.
We have 342.
Wow, that's a lot, you guys.
I know.
How do you know you have 342?
Yes, and then we put the 4 and then the baby too. See, this is Papa. The 100th place. No, this is Papa, Mama, baby.
Let's look at common visual models in math curriculums for place value. This is 6, and when it becomes 26, the 6 changes its visual model. The four-group model stays the same. 6, 26, 6, 60 has a new visual model. In the four-group method, 6. Now 60 is the same representation, the same pattern. This is 146 in a traditional curriculum. This is 146 in the four-group method. It's very complicated to do addition with common models. Did you guess that that was 27? Did you count to figure out 49? And now combining them for the answer, 76. The same problem in the four-group model looks like this. (27) plus 49 equals 76. New knowledge based upon prior knowledge is the most effective form of learning. Children who have learned the four-group number patterns use them for the conceptualization and understanding of further math concepts. For example, 8 plus 6 is 14. Let's look numerically at what the children are doing. First, they break the 6 into a 2 and a 4. Then they put the 2 and the 8 together to make 10. And 10 and 4 are 14. So once children have done it with the model, this is what they conceptualize in their mind. Making that group of 10 makes it easy to add these numbers together.
Eight plus 2 equals 10. 8 plus 3 equals 11. 8 plus 4 equals 12. 8 plus 5 equals 13. 8 plus 6 equals 14. 8 plus 7 equals 15. 8 plus 8 equals 16. 8 plus 9 equals 17.
Let's see how 8 and 6 are added in the 5-group model. When children see this representation, they are likely to take the 2 groups of 5 and put them together to make a 10, with the remaining ones combined to make the extra ones. The problem with this is what happens numerically when the manipulative is gone. They break the 6 into a 5 and a 1, the 8 into a 5 and a 3, combine the 5s, and combine the 3 and the 1 to get 14. The problem with this method is that then numerically, you would not want children to take a 5 from each number to make a 10, and then put the 3 and 1 together to make 14. This makes what's normally an easy problem quite complicated. Let's look at how multiplication is represented in most math curriculums. Kids can count the socks to find out how many. They can add the groups of socks to find the total. Or they can count by 2s. And then they need to remember that 5 times 2 is 10. In the 4-group model, we have the 5 pattern in which each square has a pair of socks. We can count by 2s. We can add the 2s and see in our minds that the total is 10. This is how the commutative property of multiplication is represented in many curriculums. It's rows times columns, 3 times 5. And if you turn the array, it now becomes 5 times 3. This is what the 4-group model uses to show the same property. 3 groups of 5, or 5 groups of 3, are the same. Another way to show it is 2 groups of 4 is the same as 4 groups of 2. Let's look at fractions. Here's a common pi example. Let's say you colored those sections. What fraction did you color? This is a 4-group model. What fraction of this model did you color? Here are some fractions, halves, fourths, and eighths, and we can see equivalent fractions easily. 1/2 is the same as 2/4. 1/2 is the same as 4/8. 2/4 is also the same as 4/8. And now let's look at decimals in the 4-group model. We have 1 in the 1 pattern. And as we get more, we build the pattern to 9. And 1 more, we move the group to the left to make 1/10. And if we have a 1 and we break it into 10 pieces, one of those pieces is a 10th. as we get more tenths and build them up to 9, when we get one more tenth, it moves to the left to become 1. 11.1 is represented like this. Doing addition with decimals is simple. Adding 12.2 and 3.3 has the same visual model in each place value to result in 15.5. Let's say we want to add 6.6 and 4.4. The 4s are added and the groups move to the left to become 11. The number line is a common visual model to teach children about positive and negative numbers. If you have this equation, you count back 4 spaces, go up the number line 3 jumps, up 2 more jumps, and down 3 jumps. Your answer is -2. This is the 4-group visual model for positive and negative numbers. We teach the kids that when you dig a hole, the hole is -1 and the pile of dirt is +1. When you put the dirt back in the hole, you end up at 0. So we represent an equation with egg cartons for the holes that are cut into the number patterns and cubes for the piles of dirt. So this equation is represented as you see it here. And now the kids start to fill the holes. 3 piles of dirt in those 3 holes, 2 piles of dirt in those 2 holes, and I'm left with 2 holes, which is -2. We represent with the numbers what we've done with the egg cartons and cubes. So the child has put the +3 and the -3 together and made 0. And then they've taken the -4 and the +2, put them together, leaving -2, and -2 and 0 is -2. Here's a picture of some of our 3rd graders with their number line from -10 to +10 working on equations. You can see it more closely here. Now let's look at another Kusky math program called Multiplication Made Easy for the memorization of multiplication facts. We first teach the kids the tens trick by giving them this example and saying, what do you notice happens to the 4, 6, and 12 when it's multiplied by 10? And the children discover the trick for themselves. 4 and then a 0. 6, 0. 12, 0. Oh, it's just the number with a 0 on the end. So now all the kids can multiply by 10. Then we teach them the 11's trick times a single-digit number. What do you notice happened to the 4 to get 44? Well, let's look. 4, 4. 11 times 6, 6, 6. Easy. The kids call this just doubling the number or writing it down twice. Now, tricky ones. 11 times a 2-digit number. What happened to the 11 and the 12 to get the answers? Let's give a hint. There's the 11 and a 2 in the middle. There's the 12 and a 3 in the middle. How does that work? The kids learn to spread the number, add the digits together, and write it in the middle. Spread the digits, add them together, and write the answer in the middle. Now the kids are hooked. They love multiplication. It's tricky. And here's the 9's trick next. What happens to the 3 to get 27, to the 6 to get 54, and so on? Well, let's look. We'll give you the 10's place digit first. Can you see what happened? Now let's look at the 1's place digit. What's happening to those numbers? The first thing is to subtract 1 and write the number down. And then take the 3 and write down what it needs to make 10. So 3 and 7 are 10's partners. 6 minus 1 is 5. 6 and 4 are 10. 9 minus 1 is 8. 9 and 1 are 10. With these tricks, learning your multiplication facts is easy. So here we go. Immunize your children. It doesn't even hurt. No more stomach aches at math time. No more tears. Kids who feel good about themselves when it comes to math. No more kids unable to get into college. Extra, extra, read all about it. We have solved our math crisis. 4-group math turns frowns upside down, and children call out, "I know, I know." We at 4-group math are raising a generation of kids who love math.